Okay, so now we want to think a little bit about the power in a circuit, and the power is an energy divided by a time. Okay, so we can just play around with dimensions and try to construct energy divided by time and connect this to the quantities in a simple resistive electric circuit and get a sense of the possibility of extracting energy from the circuit over time. In other words, generating power. So energy over time, well, where is this energy coming from when we, imagine creating an electric potential difference? We are doing some work, pulling some charged particles from somewhere and putting them onto, say, two parallel plates. Then we're doing work to accomplish this, and this involves the electric force. So dimensionally, we can say, dimensionally, right, this symbol represents dimensions of power. It involves dimensions of energy over a dimension of time. And in terms of our physical quantities, charge times electric field is a force. And if I multiply that by a distance, I get force times distance. That's a work or an energy. So this is an energy written in terms of physical quantities that deal with electric fields and electric forces. Now, if I divide that by time, I have energy divided by time in terms of quantities that involve electric fields or electric forces, charged particles, and time. And notice that charge divided by time, that's something that has to do with our circuits, right? That's a current, right? So current, dimensionally, right? The dimensions of current involve charge, Q, over time. And so we can rewrite this quantity in terms of current, but we can also notice that the dimensions of voltage, where our circuits have voltage, this involves electric field, right? If we have an electric field, a constant electric field, and then we integrate that electric field over a distance, we get something like E times D, and that has the dimensions of a voltage. So notice that what we have is that power, P, or let's just write it out. The power can be written in terms of current, I, times voltage, V. So that's current, this is voltage. And so the fact that we have a voltage and a current in our circuit tells us that we have a power. There's an energy per unit time associated with this circuit. That could be the energy per unit time that's exiting the circuit. Let's write this in a different form. Let's use V equals IR, right, Ohm's law, and write the power as V squared over R. Or we can write the power as current squared times resistance. Right, so the fact that we have a resistor in a circuit with voltage and current tells us that we have energy being released. And so we'll want a notion of how much energy there is in a circuit and how much energy we can extract, therefore, from the circuit to do work. And this is where we're headed. We're going to move towards circuits without resistors, so inductors and capacitors, where there won't be a notion of power like this because there's no resistance, and so the energy that's there remains in the circuit. And then we'll introduce resistors again, and we'll see that that energy can be extracted. There'll be, again, a notion of power, and we'll be able to quantify this.